So we can resume. The second speaker of the day will be Niklas Affolter from TU Vienna. The title of his talk is Discrete Integrability, Dimers and Geometry. Please, Niklas.
Thank you. Thanks for having me. Right. So it will be sort of a broad talk, I can tell you already. And okay, it will be partially based on joint work with Max Glick, Pasha, Pylyavskyy, Sanjay, Ramassamy, and also maybe with Béatrice de Tilière and Melotti. Why do I say maybe? Okay, when I asked what is the seminar about, so there's two themes apparently: integrability, this I don't know, trimester or something, and dimers this afternoon. Also, it's supposed to be a research talk, which in my case would somehow mean a geometry. And the audience apparently consists of physicists and mathematicians, right? So when I first heard this, I don't know, from Ariane and from Paul, I thought that's difficult to do all in one talk. So it will be, I think it makes more sense to sort of have a partial lecture. Yeah, so I guess half of it will be a bit of a lecture because it doesn't make much sense for me to present the result and you don't know, I mean, why that's interesting. And how do I do that more concretely? Well, sort of the first spot here will be a bit more of a lecture, yeah, but don't worry, I don't think many people in the end have seen this, even though it's sort of classical. I'll explain what discrete integrability is, and then I'll slowly come towards dimers, at least to planar dimers. And then it's a bit more about research. How do we connect this to geometry, both the dimers and the integrability? And okay, this will probably not exist because from experience, there will be no time for this. But in any case, there would be some outlook on other ways to have integrability in dimers. Right, you can ask me questions anytime. Yeah, that's one of the reasons why I'm doing this sort of Blackboard online talk. So I can always adjust. And, you know, I'm naturally a bit slower, so there's more time to ask questions. Right. So, what do I want to start with? Sort of a prelude, yeah, the easy thing. Like, I want to explain what, integrability is. Now, there's many definitions of integrability. There's many definitions of discrete integrability even, and I'll focus on one. And yeah, I'll start in the 1D case. Yeah, what does that mean? It means we look at the functions just defined on set, and it could be to some set. Yeah, could be the real numbers or any set essentially. And okay, that means somehow this is supposed to be Z, yeah, and they have values everywhere. Okay, but I also want sort of a rule, yeah, how these various f's are related, yeah, and in general, that just means we have a set function that goes from the set to the set, and I want that f, I don't know, k plus 1 is given as g of f of k. So it relates adjacent values, yeah, and for this to really work, I want that g is a bijection. And then I can invert this, and then fk is also given by fk plus 1 via g, right? So, okay, that's almost trivial everything here, yeah, or maybe even trivial. Means if I have some initial value here, you know, f, then this is going to be g of f, and this is going to be g squared of f. Okay, so far I guess so good. Otherwise, ask me questions. But now the real question for integrability is, what about if we look at f now on Z2 to the set? So not just on the line, but actually on the whole lattice, yeah? So we can distinguish a few cases, yeah? Guess it's going to be sort of obvious lemmas. Let's look at the first case. Yeah? If you do everything the way I just told you, which means I look at one unit square maybe in Z2, which unit squares are usually just called quads. I have some starting value here, right? Then I will have g of f here, d of f here. Then there will be g squared of f here. Yeah, so trivial, right? There's no problem in any sense. And since I can do this around one square, yeah, I could also do this for one square, then for a second. I can do this just from one initial point, get to all of Z2. Okay, but there's also non-trivial stuff. If I do this, so let's highlight this a bit. Here I had G, here I had G on the edge, here I had G, and here I had G. But now I could generalize a bit, maybe on the horizontal edges, right? I have one function G, say G1, on all of them, and on the vertical edges, I have a different function that relates my values of f. Yeah. Well, in this case, if I start with f here, then here, for example, I will have a g1 of f. Here I will have g2 of f. And now here there's a bit of a problem in the top right corner, because if I go via the sort of left top row, I'll have g1, g2 of f. But if I go via the bottom path, I'll get g2 of g1 of f, which of course in general is not the same. So here, yeah, before it was trivial, but now we have this condition. Right? And this is just already the integrability condition. Very, I think, in a very literal sense. I start with some value, I have some rule to get to the next value, which is like discrete integration. And then I do it around a cycle, or two ways, or along two paths to the same spot. And then it's not necessarily going to be the same. Yeah? So that's a condition on G for integrability. And in this case, yeah, it's just commutation. Yeah? This equation just says that G1 and G2 have to commute. All right, here, yeah. Does it make sense what I'm saying? Okay. You can also at any time like can you go back a bit or whatever, like if you feel you missed something. And then there's an even more general setup, yeah? It's like in the middle row in the two, integrability is essentially about commuting operators. But of course, you can look at even more general setup. Where you have four different operators, yeah? Maybe G1, G2, but here there's G3, G4. So there could be a different function or operator on every edge, right? And then the condition is even more general. Right, and this is the most general integrability condition you can have for 1D systems. Okay, and I'm telling you this story about 1D systems just to give you the basic understanding and to motivate why it's called integrability, because this is literally a discrete version of integration. Small disclaimer. Okay, I'm not going to write this down, but essentially 1D systems are pretty boring because everything I told you is pretty much everything you can say about them, but they occur quite a lot here. If I don't know, if Catherine would have given a very explicit definition of the height function, for example, you have to check that you can integrate that, and that would be a very basic 1D system. And also, depending on your community, usually in this 1D system, G is called a discrete connection, yeah, because you sort of got from one spot to the next. Integrability in this 1D system sense just means that the connection is flat, because it has no monodromy around the cycles, and this f function would just be an orbit of G in the flat case. Yeah. So maybe you've seen this at some point somewhere. Right. If there's no questions, yeah, we go to the next step, which is much less trivial, yeah, which would be 2D systems instead of 1D systems. What does that mean? It means we start from the get-go with a function that is defined on Z2, and okay. First, 2D systems, one usually works over some sort of field. It would also work for a set, but the field is the more common convention. And now the idea is, if I look at the quad, right, and I call these values f, f1, f2, and f12. Now there's a rule again, usually formulated as some sort of equation that relates these four values. Yeah, such that you can solve for any of them. Which really means, right, the idea is that f, f1, and f2 determine f12, right? So before the rule lived on an edge, right? Now it lives on a quad. That's why now it's called 2D, because a quad is a two-dimensional object. An edge was a one-dimensional object. And then, okay, now I looked at one quad. What if I have a bigger patch of Z2, right? Then the idea is this time I prescribe values on the coordinate axis. That would be initial data. And then I can start to propagate. Yeah, I get the value here. I get the value here. I get the value here. And so on and so forth. Yeah. So again, sort of if the lattice where I'm looking for the solution has the same dimension as my rule, there's no problem of any kind. Yeah. So what we need to do is think about one dimension more. Yeah, so what about Z3? Does this method work in Z3? Okay, so sort of a conclusion now to find this integrability condition. I want to look at the cube now, in Z3. And I assume maybe I have this given. Yeah, this is sort of the three directions, the origin and 3 directions in Z3. Well, using my rule, right? First instance of my rule gives me this point. And all right, I can also do this here, get this point, do it here, I get this point. So I sort of get the back of a cube, that's no problem. But what next, right? I mean, there's a point missing in my cube. And for example, I could use this top face to determine this point. The thing is though, I can also use this face, right? Also determine this point. But there's really no reason why these 2 points should be the same. In general, I mean, if you try some rule, some function, it will just not happen. It will be different unless you're very, very like careful or lucky, I guess. So this really is the integrability condition. You have to check, beginning with these 4 values on the coordinate axis, you have to check that if you go these 3 different ways, that you will always get the same result. And I'll explain, or I'll show you an example in a second. But that's the sort of philosophical idea. There's many motivations for this, like coming from physics, from geometry, and in some sense, even in statistical physics, where these systems occur and so on. But you can also study them just for themselves, and some people did. And in fact, they came up with a classification. They have some symmetry assumptions, that it really has the symmetries of a quad, this rule. Some other conditions that I'm not going to say, and Adler, Bobenko, Zuris, in a now pretty celebrated paper, managed to classify all these equations that are actually integrable. They come in sort of a sequence of, there's one master equation that involves elliptic functions and so on, and then simpler cases that are in some sense specializations, and the more simple they are, the more often you will see them somehow. Right, and to get a bit of a feeling for this, I want to show you explain one example. And after that, we'll move on to dimers. So what's the example? It's called polygon recutting. It's a very geometric example, which is why I usually like to pick this one. Originally, it was introduced by Adler, who did not know, or did not, at that time, did not consider this version of integrability that I'm telling you about now. Instead, back in the day, he showed that this system is integrable in the sense of Liouville-Arnold with Hamiltonians and everything. But okay, what is it? Again, we're looking at a system like this, so looking at the complex plane, and the rule is very geometric. So let's say here's our complex plane. I don't know, take one value here, one value here, one value here, 3 points of my quad, or the images of 3 points of my quad, and now I have a sort of geometric constraint. I look at the perpendicular bisector, what is supposed to be the middle, more or less, and oops, I reflect about this perpendicular bisector, and then I get my new point here. Which means I sort of take this original corner, I cut it off and glue it on again, but the other way around, which is why it's called polygon recutting, because you can do this, I don't know, for a whole polygon, and then replace, in the next step, you replace half of them. Yeah, this is a bit too symmetric, but you would sort of replace half of them, and you can iterate this and so on. Right. So the question is this integrable? Yeah, I have now a rule on quads. Can I do this in a cube? Okay, the theorem is yes, but I'm not going to prove it. Instead, I'm just going to try to show it to you. So let's see if I can make this work. Oops, sorry. So some live geometry. Let's see if this works. So F1, F3, F2 are my initial values. And now I want to do this recutting thing. I already drew one, right? So here's the perpendicular bisector of F1, F2. And I got F12 by reflecting about F. Yeah. And okay. I can also do this for this corner, yeah, F1, F3. And I wrote a tool to make this a bit faster. And I can do it for this corner, right? And so I get lots of re-glued stuff. That's a bit too close, maybe like this. Right, this would be F13. This would be F23. Let's put it all in the same color. Right, so now I have 7 points of my cube, right? And the question is, what happens if I try to construct the last one? So I have to look at the corners that are new, like F13, F1, F12. Yeah, this one. I get a new point. Yeah, this is my candidate for, oops, F123, the last point of my cube. But this is not the only corner I can take, right? I could also take this corner. Oh, and we're sort of lucky. It's here again. And I could also take, I had F3, I had F1. I could also take F2, which would be this corner. Oh, and it's also the same point. Yeah, maybe just showing you. If I remove F1, 2, 3, this B and A, they're all at the same spot. And this is not like does not depend on the initial data. I could shift this around. It's always true. Yeah, I mean, it's not a proof, but maybe it convinces you anyway. You can have some fun with this. You can even look at very singular initial data that still works. I don't know, probably can mess this up in some way. Right, yeah, so one can have some fun with this, especially if you like geometry. Yeah, questions to this?
Yeah, actually, I have one.
Yes.
So here there is a theorem, right? Was this known before? Did this have a name? This particular configuration?
I don't think so.
Okay.
Like, it's a special case in this ABS list. Yeah, you can translate this in an equation. It was not known in the original paper. It is in a paper. I think Max Glick uses it in his paper on sort of singularity behavior. But I don't know a general name for it. Also, like, I know how to prove this by a not very hard calculation. if someone comes up with a geometric argument, I would be much happier, but so far I don't know one. Other questions? Okay. Then let's return to the blackboard. So I prepared this. I thought I should do this. To prepare us for dimers, sort of, I want to explain a second point of view on these 2D systems. Yeah. Yeah, I should maybe also say these 2D systems are very well studied. There's classification results, sometimes with different symmetry assumptions. There's a lot of theory about it. Yeah. But for us, yeah, it's nice to think a bit differently about them. So prepared something already. So the left you see a cube, yeah. On the right, I want to draw something new. So what do I have? I have here F1 to F1 to 3, which means following a curve here in my cube. Yeah, that thing I forgot to label is F1 to 3. And you can think of this like a string that's sort of winding from F to F1 to 3. And now I want to move the string. Yeah, you see here F1, F1 to 3 points of a quad, and I can sort of, using my rule, I could get F2 from these 3 values. And if I draw this, I do this. So here would be F1, 2. Sorry, F2, the new value. Yeah, it's like here. There's the quad. So the blue curves that's gonna appear are like the dual graph of my cube. And that for the string, it really means I don't know. I moved it along here, and now it's here. But now, depending, you can look at the left or the right, there's a new quad appearing here. F2, F1, 2, F1, 2, 3. So I can move my string about a new quad, which on the right-hand side would be this. And then I get this new point, F2, 3. And on the left side, I just do this. So here it's still the same, but now I go up here. Then moved a bit further around my cube. And then I can repeat this. And I get, well, has to be F3. I have a new, actually, to make this picture a bit clearer, I can draw these strands here as well. That's the idea. Right, and I moved one more step. Now I took this back quad, replaced it. That's here. And okay, maybe I don't want to do all of them, or I want to rush a bit. So after F3, I would move the strand here to F1, 3. Would have the new thing here. And then after that, now sort of comes the integrability point. Yeah, now I see I have this in the background, so I can now flip it over this quad. Then F1 will appear again, right? So that would be, I don't know, here. And okay, now one final step. And I'll have F1, 2 again. And this will actually be the green strip again. You see I have F And f1, 2, 3, the endpoint of my string, but the same all the time. And now I have f1 and f1, 2 again, as in the beginning. And integrability in this setup, what does it mean? How do I view this? Well, I think of it like this. Yeah, I don't know. This string is my first state, sort of. Then I flip to get to my second state, which consists of f, f2, f1, 2, and f1, 2, 3. Then I repeat it. I have to repeat it, I think, 6 times. And then, I mean, this bottom thing is the same as the beginning, so really could draw this like this. So it means it's consistent along flip cycles. This is really what we're testing. And of course, I don't know, maybe you've seen this blue diagram again before, right? It's like, it's the braid relations. So really 2D consistency is very closely related to that. Right, question to that. Okay, so as I said, I was trying to prepare for dimers, yeah, because I want to look at dimers and think about flips, and then have some consistency there. Oh, right, and I prepared something to be not as long. Right, so this is a bit the advanced thing. So because now I'm doing multiple things at once. First of all, right, the last slide, this was still part of the 2D systems. Yeah, 2D systems meant I have a rule on 2D quads, but my initial data, so my state is 1D data. Yeah. The rule is 2D data, and the integrability is 3D. Yeah, so this is a general idea. Data is 1D, the rule is 2D, and the integrability condition is 3D. Yeah. And the very first slide I had, it was the data was 0D, the rule along an edge was 1D, and the consistency was 2D. But now you can play this one dimension higher. Yeah. Now we want to have, maybe let's make this as a remark. I want to start with 2D data. I want to have a rule that is sort of 3D, and then the problem is that the integrability check is 4D. I'll explain a bit more in a second. And I should say much less is known about 3D systems in general, in the sense that now there's only some examples known, one of which is more or less the dimer system. And then you could think about 4D systems and higher, and I'm saying this because we just had Catherine's talk, because absolutely nothing is known about 4D systems and more. No one knows any 4D system or 5D system. No one knows if they exist. And just sort of math philosophically, that seems to be related to the trouble in statistical mechanics to do anything with 3D systems. Yeah. The one advantage that exists in statistical mechanics is that you can, of course, define systems even if they're not integrable, and you can do simulations. And as Catherine showed us, you can prove some things. Here, you just, I mean, it's just a blank for more dimensions because you don't know any system. All right, that was a bit of an outlook. Let's get back. So we had the dimer model in the last talk. Now I don't remember how much Catherine defined, so I'll define a bit of stuff again. So first of all, we only consider planar graphs. Yeah, so that's exactly the case that Catherine was not doing. That is sort of easier. We look at bipartite graphs, and we also look at bipartite graphs where the degree of all black vertices is 3. That's not really necessary. That's because later I want to do geometry and I don't want to change the setup multiple times. And yeah, there's an example graph here. I also have a thing called the boundary. And yeah, that's a boundary vertex. A white boundary vertex. And we assume that the boundary vertices are all white. Right. So let's recall a few definitions. I'll make it quick because we already had the dimer model. But we have to have these edge weights. Actually, I think in Catherine's talk, they were uniform here. So they were the same on all edges. Here, there's some function on the edges. A dimer configuration, yeah. I'll say a bit more about this in a second, but you know, you have these edges, the subset of edges that is supposed to cover the whole graph. Maybe you already see that's not possible here. So I'll comment on this in a second. It would be something like this. For some reason, it doesn't cover all vertices, which I'll explain in a second. But before I do that, let's talk about the weight. So that's a dimer configuration. And the weight of that is just, so if, let's say M is this dimer configuration, then lambda of M is just the product of all the edge weights that are in there. And the partition function is classic object, usually always so Z for Zustandsfunktion, because I don't know, back then German was still cool. And you sum over all matchings and the weights of these matchings. Why do you do that? Because you want to express probabilities. Yeah. I'll not do any probability theory, but still it's motivated by that. Which means I want to have a probability for a matching. If I'm sampling matchings, and it's just going to be the weight of that matching divided by the partition. Oops, divided by the partition function. Yeah. So that way, we have a probability measure that's positive and sums to 1, and it's actually a probability measure. Right. So now, what about this problem on the left? Right. This graph that I drew, it does not have the same number of white and black vertices. So there's actually no perfect matching. Yeah, a perfect matching would need to cover each vertex exactly once. So instead, we think about these almost perfect matchings. Or almost dimer configurations. What does that mean? It still means we want to cover every interior vertex exactly once. But we distinguish a set on the boundary. Yeah, so, or maybe let's draw it like this. So here, these two, in this example, would be a boundary set I. And we'll look at partition functions that are indexed by this I. And a matching should match every interior vertex and every boundary vertex in that set. Yeah? Then you can look at these almost perfect partition functions, and there's more than one of them for each graph. And yeah, we'll see why they're relevant. Also, another reminder from dimer theory, there's a gauge freedom, yeah, for dimer configurations. Yeah.
Just to be sure, so here the boundary vertices that are not in the set I, you don't want them to be in any dimer.
Yes, exactly.
Okay, thanks.
And in this way, we make sure that dimers exist. I mean, if you choose like the cardinality of I is sort of is right, then you have an actual partition function, or at least you can have one. That is not trivial. Does that make sense?
Yes, yes.
Okay, good. Right, so we had these edge weights, yeah, maybe this edge from two vertices. But I could change them a bit by, take the same edge weight, but now I multiply them with 2 values, yeah, so values in sort of R plus. The other one is also a value in R plus. Then I get a new edge weight, and if I do this for all edges, yeah, so I have sort of a field, this mu on the vertices, and multiply all edges by this field, the idea is that nothing happens. Nothing relevant happens, yeah. Like my partition function, what happens to it, right? It's going to be my old partition function. But let's say here, look at the scaling, and here that's the vertex V. Well, now each edge is scaled by this factor mu V. Yeah. But exactly one of these edges, if I do this at the interior vertex, exactly one of these edges has to appear in the perfect matching. So really, it will just scale my my partition functions for all these that are interior vertices, and of course, if I add this set for them, it's also okay because they also have to be matched, right? It's not too important about these almost perfect matchings for the moment, but it's really almost the same as if you had perfect matchings. Okay, this gauge thing will be important later, so if you have questions, ask them now or later. Right, so that's sort of the recap of dimers. Now, still trying to get to integrability, but to get there we need flips. Yeah. Before, for these 2D systems, we had this flip around the cube. Now we need sort of 2D flips. What's the idea? I look at a small thing in my graph, a small configuration that looks like this. So a quad and 2 legs. And I can sort of forget about the interior, delete it, and glue almost the same thing in, but rotate it like this. Yeah. And now you can formulate this in different ways. I'm doing it sort of the other way around. So first of all, to make it a bit simpler, I assume a special gauge. Yeah, that's not necessary, but if I reach the end of my talk, it can make a nice relation, and either way it helps with calculations and understanding, I feel. The idea is I have functions, this tau field, which is defined on the faces of my graph. Yeah. And now the edge weight, lambda of this edge, is supposed to be 1 over the 2 adjacent face values, yeah, face taus. And now I have this replacement, yeah, so replacement or the flip, that's this special flip is called the spider move. And then I want to leave everything the same except I want to change this variable. And here the rule that we had before, like, I mean, we always had rules for these flips, and here we have a new rule, and it's this. Right, and okay, I could just postulate this rule for whatever reason, but there is some motivation behind it. Since I'm not that great on time, I'm just gonna tell you. So the idea behind that is that if I do this, the new partition function is gonna be, or the old one is the new one just multiplied by one variable. But that, of course, means that probabilities for matchings. Yeah, unchanged is not completely true, but somehow so maybe I should not say this, but almost all probabilities and correlations are unchanged, except if they involve edges right here, which makes sort of sense because the partition function is not changing. And right, I didn't say this before, but the idea is also that you can get probabilities by taking derivatives sort of with respect to all the edge weights that are involved. So this would have to be many edge weights here in the matching on the left. Yeah. So that's usually the idea. You get probabilities from taking derivatives. Yeah, it's not very strict here, but of partition functions. How you check that, and also how you see that it's a bit difficult to explain this, is as follows. So I'm not going to do the calculation, just explain the idea behind it. You look at matchings before and after. For example, here, these two edges could be in the matching. Then I do this replacement, this flip. And now I see, for example, there could be, I could instead glue in these two edges in the matching, yeah, but still form globally a matching. But there's also another one. That looks like this. And then you can calculate the weight of the configuration on the left and the weights of the configurations on the right, and they will, on the right, they will sum up to the same thing as on the left, except for this factor. And then you have to look at all the other possibilities. Oops. For example, it could also be something like this locally. Then there would be one possibility on the right, and so on. And that's sort of a calculation exercise. So that was the original motivation behind this move. Yeah, it wasn't to show integrability or anything. It was just to change a bit without changing the partition function in a significant way. And this is called, this phenomenon is called Z invariance. And there are other models except the diamond model where this also exists. Yeah, but we are focusing on the diamond model right now. Okay, so this was a bit vague. So maybe if you have questions, ask them. Maybe it's clear. All right, there's a second simpler flip. So I'll just put it on this slide as well. That's the only other flip we need. And that is the so-called resplit. The idea is we have this local configuration and we replace it like this. Right? And what do we do with these phase variables? The answer is easy, we just don't do anything. Yeah, so the lemma here is also Z invariant. I think concretely it's something like okay, and now we're almost ready, or I think now we're ready, yeah, to get to integrability. Yeah. What do I mean? Well, back to the example graph that we have here, right? Let's start out with some edge weights and this special gauge. You have tau variables everywhere and so on. And now if I look at this graph, you see here in this phase, I have this configuration where I can apply the flip. This the first flip, so the spider move. Let me show you what happens. So it's here where we apply the spider move and glue in this new thing. Well, the rest we just leave unchanged. So here's where we perform the move. Oops, there's a mistake in here. Sorry about that. There's one more vertex here. So this is what we did. Yeah. Right. But now you see there's another spot where we could do something. Here we could have this configuration. Yeah. Let's just see again. This configuration where we can do the other type of flip. So what happens? This vertex here. Now we glue in the other thing. All right. Now, I could do this for a long time and take a while, so I'll just explain sort of directly what's happening. Let's compare these two graphs. Yeah, the top graph, or the first graph and the third graph. Can sort of start here, call this the 1, 2, 3, 4, 5. Now, call this also 1, and this 2, 3, 4, 5. The point is, these are the same graphs. Yeah, the first graph and the third graph are the same, but they're rotated. In fact, right, one moves 2 steps sort of in positive direction. So it's a rotation by 2/5 of 2 pi. Which means if I play this game more and more, yeah, for example, now in the next step, I could apply my spider move here. Then do this and then do it more and more often. After 10 steps, yeah, 2 steps made rotation by 2/5, so 10 steps will make a complete rotation. I will return to the same graph that I started with. And all the time I left these partition functions invariant. So that's sort of all these partition functions are preserved. That's nice and all, but is it really the same system? And the thing is, one can show that actually tau 1 and tau 2, right, the boundary taus aren't changed anyway. We always only change those that are in interior phases. They're the same again. Which is really not trivial. No. I applied this rule down here 5 times. Yeah, the other 5 times just nothing happened. And I went around this flip cycle. Now each state was a 2D object, and each step related to 2D objects. And at the end, I get the same again. Yeah, particularism, it also means the edge weights are the same. Yeah, and this really means, at least for me, this is the reason dimers are integrable. Planar dimers are integrable. Yeah. Because you can apply these local moves any way you want. And if you get back to the same graph, yeah, in a disk, then you get the same diamond model again. Yeah. This would not be true for a general model and a general flip or whatever.
So this cycle of flips that brought you back to the original graph.
Yes.
So it should be thought of as like something that lives in 4D in some sense, like on
Yeah,
some
that's a good question.
polyhedron.
So the thing is, okay, so I try to explain, but it's just not easy to explain, even among specialists. The idea is that you have this 2D object. Doing one step is like moving in 3D, like the first red thing. But it's not as nice as before where we were just on set n, because let me draw this here to explain this a bit. Let's take a different color. Here, right, I had my initial 4 values, say tau 1, tau 4, tau 2, and tau 3. And somehow I have a value tau down here. And then I replace tau by a new value, tau tilde. So the combinatorics of this thing, I don't know if you can see this, is an octahedron. So the 3D thing is made up of lots of octahedrons instead of cubes. And the claim that is hard to see is that what you're doing here, I mean, from here to here is one of these octahedral flips. But if you go around the whole thing, you're moving in the 4-dimensional octahedral lattice. You're sort of flipping your 2-dimensional surface and your 4D.
It's a bit hard to visualize, but
exactly. Yeah, you can maybe, the 3D lattice can still be visualized because you have all these octahedra, and then you would have another one here. So on, you get this honeycomb lattice. Between the octahedra here, there's a tetrahedra, but otherwise you get all these octahedra. And I mean, even that 4 is not really visualizable, right? We sort of believe it because of our intuition. But and that's one of the reasons why this flip view is so nice, because I can draw 2D slices and I can draw sequences of 2D slices, and the ambient dimension is not so important. Right. I don't know. Does it help a bit?
Okay. Well, I'll believe you for the 4D part. But,
okay,
yeah,
thank you.
I see a kind of 3D step. Yeah.
Yeah, there's no easy way to explain. We can concretely write down this embedding into the 4D lattice, but it takes a while, so I'm not going to do it. Let me also give a bit of a disclaimer. This equation, so first of all, to show that this lattice and view and this graph view are the same is not so easy. On the graph side of things that I explained to you right now, Dylan Thurston back the day actually showed under some minimality constraint that the flip graph is connected in general. So you can get from some configuration to another by flips. And he had a conjecture about these cycles, right? Because what I did was show you one cycle, but it's not clear that all cycles would be of this nature. And Dylan had a conjecture, and actually it was proven, I think, now 3 years ago by Blitzky and Wellman. Yeah, so they essentially analyzed these cycles in the flip graph, and the answer is, even though I only showed you one, it's essentially the only one that's relevant for us. So I did sort of show the whole thing, even though we don't know it. And this equation, this equation that we had, tau tilde tau plus, equals tau 1, tau 3 plus tau 2, tau 4, is also called the discrete Pylyavskyy equation, which is also known as Hirota-Mive equation, yeah, depending on whether you ask Russians or Japanese people. And if you ask American people, it's called the octahedron recurrence. And that because it has been rediscovered several times in different contexts. You can also formulate this multidimensional or this integrability in terms of a lattice, yeah, which was done again by Adler, Bobenko, Zuris. But that's practically unexplainable to anyone because yeah, you have to work with 4D lattices. Right. So I don't exactly remember when we started. We started at 6, right? That means I have 1 minute.
Yeah, roughly 1 minute. Yes.
All right. So I finished sort of the lecture part, which is not so trivial. And so I'll just skip the geometry part, I think, in general, and instead just end just talking for a minute a bit about integrability in general on dimers. If you replace the sort of the disk by the torus, then one can make these partition functions into Hamiltonians, yeah. And you have a natural Poisson structure, and you can show that you like Goncharov and Kenyon showed that you get the integrable system in the very classic sense. You can there's a result originally by Speyer that you can sort of explicitly describe how these taus change under flips for certain graphs, and you do it by using partition functions again. So sort of these preserved quantities we have can be used to exactly solve the recurrence, which sort of makes sense, but it's highly non-trivial. With Paul and Béatrice, I did it sort of for the geometry part. There's a second recurrence there that's also solvable by dimers. If you do this solution stuff, you also see that these recurrences, like algebraically, as rational maps, the degree grows way too little. It's called sort of algebraic entropy. It's another definition of integrability. There's some special stuff about how the singularities behaves, which would be also a sort of discrete version of integrability, which you can also analyze via dimers and so on. And that's it. Then I'll just finish the talk here. Thank you.
Thank you very much.
Thank you.
Thank you. And I think it's a good time to ask if are there questions from the public.
I see a question in the chat. I don't know who introduced partition functions.
Yeah.
That was by you. Yeah, I don't know.
Yeah, this was when you were mentioning the Zustat sum and yeah, like.
Yeah. I mean, I know it's called Maxwell-Boltzmann statistics essentially.
Yeah.
So, but I don't know who was first.
Yeah. Other questions?
So you mentioned at some point that you were just talking about dimers as a like 3D integrable system because
Yes.
we asked you to talk about dimers.
Yes.
So could you say a few words about which other types of models seem related to that?
So we had this equation, yeah. I'm not going to write it in detail, but type this, which is called associated to octahedra, and on like here would be the statistics side. Here would be actually the other math physics people who do not do statistics. some group of them. They came up with this, I think, first. Then it turned out it's essentially this consistency for dimers. There is an equation like that. So this was for the octahedron. There is an equation like that that involves, looks almost the same, but then has two more, and it involves the cube. Yeah. And this is spanning trees. So the spanning tree model would be on this side of the thing. And then there's one more which I cannot write down. It's much more complicated, but it also involves the vertices of a cube. It's so I didn't give names. So the first one, okay, octahedron recurrence. The second one would be the cube recurrence. The third one is usually called the Kashev recurrence. I guess because cube was already occupied. And on the other side, I mean, Paul could tell you this is not exactly true, but it's more or less true. It's the Ising model, yeah. So the Ising model definitely features this weird equation on the left. Yeah, personally, I think it's especially interesting because there's this notation where this is called discrete KP. This is called discrete B KP, and this is called discrete C KP, and it's motivated by continuous theory, and this really refers to the Lie algebras. This could also, if you want, called DAKP.
So are the B, E, and C related to deformations of KP, or?
No, it's just originally it was thought that these are three different equations that are superposition principles for the continuum solutions of the continuous versions of these equations. And I mean, on the continuous side, there's a reason for A, B, and C. I mean, nowadays, because there's this template trick that shows you can model spanning trees more or less by dimers. And there's sort of this Dubedar or other people trick, modeling the Ising model via dimers. One can replicate this here.
It only works for very special, like the Ising model and very special types of graphs, right?
I mean, you can take any Ising graph, any planar Ising graph, and get a dimer graph from it. But only special dimer graphs.
Okay, it's on the dimer side that you have
that it's specialized. So if I can add a question, yeah. No one really knows what that is, and also if it exists, and it should exist, there should be a force model, but it's unclear what that is.
Yeah, so like if I understand correctly, this notion of integrability that you presented, like it manifests in only very specific statistical mechanics models.
Yes,
because...
I mean at least the 3D thing, yeah. If you only want like 2D stuff, then I think you can. Yeah, I'm not a specialist, but like I don't know, percolation, for example, would not be a 3D integrable system. But
the 2D one?
But there is a constraint. I think maybe it's the critical case or something like that, where you can do flips, but this constraint that it's critical makes it a 2D system because you cannot have free two-dimensional data, so it's like a 2D system then. And I assume this is true for other systems.
Yeah, I guess like in general for like statistical mechanics models on 2D, like the context in which you have a really nice structure is at the critical point. Otherwise, in general, you don't have something I don't know, related to
Yep.
DCFT, etc. And maybe I can also ask if you want like to mention things that you did in relation to everything that you presented. Because
Yeah,
we
sorry
don't have a
about
lot of
that.
time for that.
Very quick though, geometry. So the idea is that we assign, you know what, I did a trial run of this. So I have some slides that are actually, don't look so nice, but are finished. So the idea is to assign maps to projective space from your, right, you had this graph here. You assign maps that satisfy some constraints, some incidence constraints to, as a map to the projective space. And then you can see that there's a linear algebra description for that via vectors and so on. And turns out it has some gauge freedom. It's the same as the dimer model. It turns out you can apply flips to these geometric maps. They're compatible with the dimer model. So the dimer partition functions will automatically be preserved quantities of these geometric models. These tau functions that I used, one can, there's certainly a nice geometric way to see them as certain determinants, which is related, no, never mind. Right, so I would have given you a bit of a background in that, and then that's also related to sort of modern approaches in statistical mechanics via these T embeddings, as like embedding stuff that's sort of geometric. That is essentially, that was not the original goal, but it's closely related to that, and you know, stuff that the idea is it captures very generally lots of examples in the literature done in statistical mechanics, but also, you know, especially in the US, there are all these people who do like pentagram map and sort of geometric dynamical systems that they show are integrable in a continuous sense. And using this framework that we developed, you can actually show that you have all the examples, you put them as a special case of this framework, you use what Gonchov and Kenyon did, having a general integrable system using dimers, and you get all these results sort of for free if you know the right links and so on. That would be what I worked on and still work on.
Okay. Thank you also for this overview. And are there other questions from public? Okay, if not, I suggest to thank again Niklas for his talk.
You're welcome.